Today's lesson focuses on two common relationships that we see in gases. So the first relationship we want to talk about is Avogadro's law. And we remember Avogadro, he is the man responsible for the mole concept. So it's no surprise that he is coming up with a law or a relationship dealing with moles with gases. So he says that as the number of moles increases of a gas, so the amount of a gas, that the volume also increases. And this is a direct relationship. And when we see direct relationships, again, we have the variables divided out by each other, similar to those other gas laws that we noticed a couple lessons back. So doubling the number of moles of a gas will also double the volume of the gas and vice versa. If you decrease the moles by half, then you'd notice that the volume would decrease by half. So it's a nice relationship. And again, this is assuming that pressure and temperature remain constant. So it says, for example, adding twice the number of moles of gas to a balloon. So again, if it's twice the number, you're doubling the number of moles, you're going to double the balloon's volume. Avogadro's law can also be used to predict the volume of reactants and products. This is actually a really handy relationship because in a balanced reaction, we know that the coefficients relate to mole quantities. So this can also just tell us what the volumes of each of those gases would be as well. So here's an example of using Avogadro's law with reactions. So here is the reaction to produce water. And the key thing here, this only works if your states are gases, okay? So this relationship does not work if you have a solid in there or a liquid. So what we know is that if we're looking at the coefficients, the moles of everything, we have 2 moles of hydrogen, we have 1 mole of oxygen based on these coefficients, oxygen. And then we have 2 moles of water. And this is a direct relationship to the volume. So if you were looking at this reaction, you would know that you would be reacting 2 liters of hydrogen or 1 liter of oxygen or 2 liters of water would be produced. And from there, you can scale up or scale down those quantities, but it's a direct relationship to the mole, fixed mole quantities in your reaction. So let's try a couple examples of using Avogadro's law. It says if I fill a balloon with 5.2 moles of gas and it creates a balloon with a volume of 23.5 liters, how many moles are in a balloon at the same temperature and pressure that has a different volume of 14.9 liters? Well, we're going to set this up and we're going to use Avogadro's law. So N1 over V1 equals N2 over V2. And when I read this, these two go together, right? So I have 5.2 moles with a volume of 23.5 liters. They're asking us to solve for the new amount of moles, right? How many moles? If they change the volume to 14.9 liters. So just make sure that your volume units match. It could be milliliters, it can be liters, it doesn't matter. And then we're just gonna cross multiply our 14.9 up and over, divide out the 23.5, and then we're going to solve for N2, and we're gonna get a mole value of 3.3 moles, keeping with 2 sig figs based on this initial mole value that we have here. The next example says what volume of oxygen is required to react with 125 liters of hydrogen to make gaseous water. So here, when you realize you're dealing with a reaction, all you've got to do is write out that balanced equation that we saw on the previous slide. So you'd have 2 moles of hydrogen reacting with 1 mole of oxygen to make 2 moles of H2O. And again, this only works if all the states are gases. So we're looking at this relationship right here. It's a 2-to-1 relationship. So you could solve this a couple of different ways. So when you realize that it's a 2-to-1 relationship, remember that the moles and the volume go hand in hand. So they want to know what is the volume of oxygen if they're using 125 liters of hydrogen. And we know that this is going to be a division of 2 because it's a 2-to-1 relationship. So you can think of it that way in your head. Sometimes they're not so easy to set up. And so we need to set up Avogadro's law. So if you want to use Avogadro's law, you're going to have to set up that formula just slightly different. So watch what I do here, because I can relate this now to both of these reactants. If I set this up and I say that the moles of oxygen and the volume of oxygen is related to the moles of hydrogen, we know it is, and the volume of hydrogen, then I can solve for the volume of oxygen in this equation. But I don't want to solve for volume of oxygen in the denominator. So what I'm going to do is I'm going to flip both sides, right? Because I'm after this variable and I don't like it in the denominator. So we're just going to flip that so that I get volume of O2 over moles of O2 equaling, got to flip both sides, volume of hydrogen over moles of hydrogen. And now I can sub in those values from the reaction and the data that they give me. The volume of oxygen is what I'm solving for. I have 1 mole. Oops, I've lost my marker. 1 mole. Here, I'll do it over here. Volume of O2 is what I'm solving for. I have 1 mole of O2 from the balanced equation. They told us that we are going to react with 125 liters of hydrogen. And I know from my reaction that that would be the equivalent of 2 moles of hydrogen. And so what I'm doing is I'm just going to take my moles, 1 mole of oxygen, cross multiply it, nothing changes. And then I'm taking 125 divided by 2. Again, we saw this in the original reaction. You might be able to do it in your head. If not, you got to set it up this way. And we come up with a volume of oxygen of 62.5 liters. The second commonly used relationship in gases is this concept called molar volume. And the molar volume of a gas represents a constant volume of 1 mole of gas particles. Okay, very similar to molar mass, where molar mass was the actual mass based on, or sorry, a constant mass based on 1 mole of gas particles or any kind of particle, it didn't matter. Molar volume is the same for all gases at the same pressure and temperature. This is different than molar mass. Molar mass had different, amounts depending on whether you're dealing with hydrogen or helium or sulfur. Now the molar volume of a gas is always the same. And it is easier for us to measure volumes rather than masses or amounts, right, of gas molecules. So we tend to use volume more often with gases. Here's the formula that you need for molar volume. So again, this is our constant right here, and we're going to learn the 2 constant values in a second. And then these would be our actual volumes and mole values depending on the conditions that you set up. So we only deal with molar volumes at STP and at SATP conditions, and they're always the same volume. Okay, so if you have STP conditions, so standard temperature and pressure, 0 degrees C, 101.3 kPa, if you have 1 mole of particles, they're going to take up a volume of 22.4 liters. If you go up to SATP conditions, where the temperature increases to 25, pressure comes down to 100, if you have 1 mole of gas particles, they're going to take up a volume of 24.8 liters. So let's try a couple of examples using molar volume. And the first thing we want to do is just write that formula down again. So molar volume, we use this symbol, capital V with a little m after, and it's equal to actual volume over the amount of moles. So we can use this formula only if we have STP and SATP conditions. So here it says what volume is occupied by 0.024 moles. Okay, so not 1 mole. Remember, this is for 1 mole of substance. Now we're changing that. So we want to know what's the actual volume. So we write out our molar volume formula. So Vm equals actual volume over moles. And we want to figure out the actual volume of CO2 gas. And we're going to equate that to the molar volume times the mole value. So the molar volume at SATP is 24.8 liters per mole. We don't have 1 mole. We have 0.024 moles. My mole value, or my mole unit rather, is going to cancel out. And then when I multiply these two together, I'm getting an actual volume of 0.60 liters, rounded to 2 sig figs. So it's as easy as that. Here's another example. It says if the mass of a propane tank drops by 9.1 kilograms after 1 month of use, what volume of gas at SATP was used for cooking? So again, if we're going to use this formula over here, I need to know the mole value. And they didn't give it to me, but they gave me the mass of propane. So what we'll do is just off to the side, we're going to calculate the moles of propane. Oops, sorry, CH8, by taking mass over the molar mass. So they gave me 9.1 kilograms. So we want grams. You're going to multiply that by 1,000. So you get 9,100 grams. And then we're going to divide by the molar mass of propane, which is, give me a second here, 44.11 grams per mole. So I get a mole value of, it's going to be big because I have 9,100 grams divided by 44.11. I have a mole value of 206.302 moles. So we want to know what's the actual volume of the gas. So if we're going to rearrange, so actual volume of propane, we want to rearrange our molar volume formula to give me molar volume times moles. This is at SATP conditions, so I know that it's 24.8 liters if I have 1 mole. I do not have 1 mole, I have a lot of moles, times 206.302 mole. And then we're going to multiply this through, and I get a huge value. I get 5116.30 liters. I need to put this into 2 sig figs. You can go ahead and put that into scientific notation if you want. I'm going to divide by 1,000 because I don't like scientific myself. And I'm going to say this will work out to be 5.1 kiloliters. Okay, that's an option. Otherwise, put it into scientific notation.